We've got a curved mirror up on the board right now. Tell me what kind of mirror that is. It's concave. What's another name for concave mirror? Converging, right. Why do we call it a converging mirror? The other kind, by the way, is called diverging, right? So converging versus diverging. Why is this one called converging? It describes the behavior of this, right? What it does. Patrick? Not all the rays converge at the focal point, but all the rays that are parallel to the principal axis converge at the focal point. So if we draw one up here, it's going to go down through the focal point. One right here, it's also going to go down through the focal point. One down here, it's going to go up through the focal point. So we're going to label this little point F right there because that's where all the rays parallel to the principal axis will go. What's this little dot right here? If this is F, the point where all the rays parallel converge, then what's this one? What is it? Dan? Yeah, we'll call it the center of curvature. It would be the radius of the mirror. If we made this mirror into an entire circle, that center of curvature would literally be right in the middle, right in this geometric center of that mirror. What's the relationship between the distance from the mirror to F and the distance from the mirror to C, the center of curvature? F is 1/2 of C. So if the radius of the mirror is 10 centimeters, then the focal length of the mirror is going to be 5 centimeters. If we show you the video like I showed you yesterday of the Simpsons movie, the middle of the mirror, the center of curvature of the mirror, would literally be halfway across the town of Springfield. Therefore, the focal point would be 1/4 of the way across the town of Springfield. And that's why we saw yesterday, right, when Homer was standing really close to the mirror, the image that was produced should have been a bigger image, because we know that he was inside the focal length because he wasn't 1/4 of the way across town. All right, there's a couple rays, there's actually 3 rays that we can draw here on this mirror to determine what the image looks like, but there's only ever 2 that we need to draw. Let's put an object right here in between F and the center of curvature, and let's draw a ray diagram for that one. The first ray that we're going to draw is going to be from the top of the object parallel to the principal axis, and then it's going to go down through the focal point. Where's that second ray go? Remember, there's 2 other options for rays to draw, but there's one that's easiest. So we'll always pick that one we can at least, Dan. Yeah, it's going to go from the top of the object to the focal point. It's going to strike the mirror. When it strikes the mirror, it's going to reflect back parallel to the principal axis. Where they converge is where the image is formed. Since those 2 rays are both reflected rays, and since they both come from the same spot on the object, they count as intersecting. 2 solid lines are intersecting here. What does that tell us about the image if it's 2 solid lines that intersect? It's a real image, right? It's a real image. It can be projected onto a screen. Now, that doesn't mean we are projecting it onto a screen, but we could. If we were to put a piece of paper right here, okay, perpendicular to the board here where you see that arrow, you would see what an image of whatever that object is on that screen. But you'd see it upside down. That's the second characteristic, right? It's real, it's inverted. And you would also see it larger than the object. It would produce an image that's bigger than the object. So we've got real, we've got upside down, and we've got bigger. Let's try another one here. This time, let's put our object in here. This is really, really close to the mirror. Remember that very first picture that I showed you when we started doing the curved mirrors? There was a guy standing right in front of a concave or converging mirror. Remember what the image of his face looked like? It was huge, right? You couldn't even see his entire face in this giant mirror. It produced a very, very large, upright, virtual image. Let's take a look and see if that's what we get when we draw this ray diagram. First ray is going to go from the top of the object parallel to the principal axis and then down through the focal point. Where's that second ray going to go? This one's a little bit trickier than the one we did in the last picture. Where's the second ray going to go? Okay, up here somewhere? Like where up there somewhere? Up, as if it's going away from the center, good. It's going to reflect back upon itself like this. They don't intersect over there, so we're going to extend those reflected rays This one goes up here. This one goes up here. They're going to intersect over here. Two dotted lines intersecting this time. Therefore, we know that it's a virtual image. We know that it's upright based on the orientation that you see there. And we know that it's also larger. It's exactly what we should see. Hey, we look at that picture that we saw at the very beginning of this section of the unit. The guy looking in the mirror. We saw an upright, bigger, albeit much bigger, virtual image. Good? What's this kind of mirror called? This one's a diverging or a convex mirror. It doesn't matter where we put our object here. We're going to get the same characteristics. First ray is going to go parallel to the principal axis, right? Then it goes down through the focal point. Is that right? Can't go down through the focal point because this is a mirror, and when the ray of light strikes the mirror, it's going to reflect. So where does it reflect? Down through a focal point on this side? If it did, that would be a converging mirror, and that's not what we have here. This is diverging, so let's get rid of that one. Where's it going to reflect then? It's going to reflect not away from this one, okay, not away from that, because that's the center of curvature. Rather, it's going to reflect away from this one, away from the focal point. So it's going to look something like this. The second ray is going to go from the top of the object down toward the focal point. It's not going to go all the way there, because when it strikes the mirror, it's going to reflect. It's going to bounce off. It's going to bounce off parallel to the principal axis. They don't intersect, so we've got to extend those as well. This one gets extended back to the focal point. This one gets extended back parallel to the principal axis. We've got two dotted lines that converge right there. What does it tell us about the image? It's what? It's virtual. Dotted lines mean it's virtual. We couldn't project it onto a screen even if we wanted to. It's smaller. Yeah, you clearly see that it's quite a bit smaller than the object is. And you can see that it's upright as well, right? Right side up. Every time you look in a convex mirror, a diverging mirror, you will see slightly different sizes of images, but the image is always going to be smaller. It's always going to be upright, and it's always going to be virtual. Yesterday, we introduced the two equations that we do with this whole curved mirror thing. We had 1 over f. First one, the mirror equation, 1 over f is equal to 1 over do plus 1 over di. And then we had m is equal to hi over ho equals negative di over do. What did f stand for? The focal length, the distance from the mirror to the focal point. Do stood for the object distance from the mirror to the object. Di from the mirror to the image. Hi? What's h stand for? The height of the image. Ho is the height of the object. What units are we going to use for hi, ho, do, di, f? What units do we use? Anything you want. Okay, as long as it represents a distance. Usually it's going to be centimeters because that's convenient. But it could also be meters. You want to use meters? Go ahead. You want to use kilometers? Go ahead. You want to use light years? Go ahead. It doesn't matter what units you use for distance as long as you're consistent through this entire problem, okay? What units would m have, by the way, the magnification? Why not? Right. Centimeters over centimeters gives me 1, right? They cancel out. So there's no units associated with the m. Sometimes you do see it written as, you know, like the magnification is 2x, 2 times, but you don't need that. If you just say m is equal to 2, that would be just as correct. This big table yesterday is pretty much where we finished it off, other than an example problem. We had to identify when these variables were positive and negative. Let's start off with a different variable this time. Let's go ho, hi, do, di, and f. Different order of these variables this time. Ho and hi kind of go together. Ho and hi, whether they're positive or negative, are based upon what? What determines whether ho and hi are positive or negative? When is ho going to be a positive number? When it's right side up, when the object is right side up. And that's going to be the case most of the time. It's going to be negative when we have an inverted object. Hi is going to be the same general idea. It's going to be positive when we have an upright image. And it's going to be negative when we have an inverted image, an upside down image. We see an inverted image quite often. We don't see an inverted object all that often. Okay, it's not a big deal if we do, just make sure you make it negative if it is. DO. When is DO positive? That might have been a bad one to do first in this group of 3 at the bottom. DO is always positive. Why? Because DO is always real for us in Physics 30. It's not based on whether it's right side up or upside down. It's based on whether it's real or virtual. And for us, DO, the object distance, will always be real. So DO is always going to be a positive number for us. DO is never going to be a negative number. DI, it's positive when you have a real image. And it's negative when you have a virtual image. When is F positive? When you have a real focal point. And it's negative when you have a virtual focal point. Anybody tell me when you have a real focal point, though? We draw array diagrams. We can see whether it's a real or virtual image. How do we tell whether it's a real or virtual focal point? Might seem a little bit trickier, but it's actually easier. You always have a real focal point if what? No. Sorry, if the focal point's on the left side? Yes, in the context of mirrors, if the mirror is facing the left side. Yeah. Let's stay away from that reasoning, though. When we go to talk about lenses and real focal points and virtual focal points, it's going to be exactly the opposite, actually. So let's not define it in those terms here. Yeah, if it's a converging mirror. If it's a concave or a converging mirror, it's going to be a real focal point, therefore it's going to be positive. If it's a diverging mirror, we're going to get a virtual focal point, a negative value. Finally, the last one, M, the magnification. When's M positive? Good. When the object and the image are on the same side of the principal axis. If you've got the object above the principal axis and the image above the principal axis, then M is going to be positive. If they're both below the principal axis, they're both upside down, then it's still going to be a positive magnification. But if you have one that's upright and one that's inverted, then you're going to have a negative magnification. All right. We gave you a few questions to work on yesterday on page 664, 5 of them, in fact. Pretty sure we're going to need to go over number 5 here. Is that right? Any others besides number 5? Got to be something here, Dan. Okay. Okay. The question from Dan was, how do you find out whether it's an upright image or an inverted image without knowing what the height is of the image? Is that right? Okay. Generally, there's three ways of finding out whether the image is upright or inverted. Okay, one of the ways is getting the image height, and if it's a negative value, it's inverted. If it's positive value, then it's upright. Okay, so let's say you can't do that for whatever reason. That was your question, right? If you can't do that first one, then what do you do to find out if the image is right side up or upside down? Let's look at the magnification next. The magnification is a positive value if the image and the object are on the same side of the principal axis. So assuming the object is upright, which it usually is, a positive M would indicate an upright image. A negative M would indicate an inverted image. If you can't get M, the only other way to do it, besides finding HI or finding M, is to draw a ray diagram. Okay, draw that ray diagram roughly to scale and see what it looks like. Okay, usually we can avoid that, though. Usually we don't have to do that. Okay, sometimes you might be stumped a little bit mathematically, and you might say, I'm not sure what to do. Okay, draw a ray diagram. Usually, though, there's somewhat of a trick to avoid having to draw the ray diagram. Okay, we'll do number 5. There's no others besides number 5, you sure? Okay. This one says, light from a distant planet is an incident on a converging mirror. That means it's a positive focal point. The image of the planet varies or forms on a screen 45 centimeters from the vertex. That's going to be DI, the image distance. Find the focal length of the mirror and the image characteristics. We'll worry about the focal length first, and then we'll try to identify the image characteristics. I want to find the focal length. There's really only one equation that we can do or use to find the focal length. 1 over f is equal to 1 over do plus 1 over di. We're finding the focal length here. The object distance, not quite sure what that is yet. The image distance, 45.0 centimeters. We need that object distance in order to plug into this equation to get f. How far away is this planet? We don't know. We don't know. Let's say it's 1 million kilometers. Okay? I mean, it could be any one of a huge range of numbers, but let's say 1 million kilometers. It's a big number, right? If we want to convert that to centimeters, because the 45, the image distance is in centimeters, then let's do that. 1 million kilometers is the same as 1,000 million meters. 1,000 million meters is the same as 10,000 million centimeters. No, it's 100,000 million centimeters. So if our planet is 1 million kilometers away, then it's 100,000 million centimeters away. That's a giant number. I'm not even going to bother putting the number 100,000 million centimeters away. That's effectively infinity, right? It's so far away relative to this 45 centimeters, it just doesn't matter. What's 1 over infinity? 0. What's 1 over 100,000 million? Well, it's not 0, but it's pretty darn close, right? 0.00000000000, and so on for a long, long, long time. That first number is pretty much 0. If that first number is pretty much 0, then the equation becomes 1 over f is equal to 1 over 45.0. Rearrange that to solve for f, we get 45. We got a focal length here of 45 centimeters, same as our image distance. Why? Because ultimately, you get light coming off a planet that's that far away. There's rays of light coming in every which direction, but the ones that actually hit your mirror, if they travel that far and are still only this far apart from each other so that they're able to hit your mirror, then they've got to be pretty much parallel to each other. Where are they going to converge? At the focal point. So df is going to be the same as f. What about the characteristics now? If we draw a ray diagram for a mirror where we have this as our focal point, this is our center of curvature, and this is our object, we produce an image that's inverted. If we bring this out, okay, this object, way out here, we're still going to produce an inverted image. If we bring this object way, 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 way out to where this planet is, then we're still going to produce an inverted image. As long as we're beyond twice the focal length of the center of curvature, the image will be inverted. Now, by this ray diagram, we can also determine that the image is going to be smaller, but we can also figure that out mathematically. Let's say m is equal to negative di over do. Negative 45 centimeters. What was do again? 100,000 million, or whatever number you pick that's huge, basically infinity. I don't need to solve for that magnification, the value of that. It's going to be a really, really, really small number. Because it's a number between 0 and 1, that means the image is going to be smaller. And because the magnification is negative something, it means the image is going to be inverted. Upside down. How many people got that question? Good. That's a tough question. That's a challenge question. There's no doubt about that. Okay. You can do all the mathematics in the world and be really good at questions 1 to 4 and the worksheet that I'm going to give you in just a minute here. And that's great. Okay, that's going to help you with the vast majority of questions that you'll ever see with this. Okay, but that's that next level of question where mathematically it's not all that bad, but you got to do some thinking to get there. Is that the logic you guys used? Or did you think of something else? Okay. Austin? Okay. Be careful with that. Okay, be careful with that. Because obviously when you get a test, they're not going to tell you what the answer is, right? So working backwards doesn't usually work out that way. All right, I'm going to give you a worksheet right now, and I'm going to give you just a couple of minutes here, maybe about 5 minutes to work on that worksheet. Maybe get a question done, give you an opportunity to ask me a question as you work. Then we're going to move on to our next topic. I'm going to draw a picture for you to introduce the next topic. If you had me in Physics 20, you would have seen this picture already. When we talked about refraction, we defined it as the bending of light, the bending of a wave. Okay, we did a little analogy in Physics 20, in my class at least, where we had a parking lot that was paved with asphalt. And then we had the swamp over here. Maybe the water is, you know, a meter deep, whatever. For whatever reason, I still haven't figured out exactly why, but for whatever reason, we've got a bunch of soldiers in this parking lot, and they're all standing right beside each other. If we're looking at these soldiers from above, then they might look something like the crest of a wave or a wavefront. 5 seconds later, these soldiers are going to be marching forward in this direction, so their position will have changed. 5 seconds later, because these soldiers march in stride, they're all going to be roughly in the same position north of where they started. Except for this guy. This guy hasn't traveled quite as far in that 5 seconds. Why not? He's gone into the swamp, right? He's in the swamp now. He's walking in the swamp, but it's a little bit harder to walk in the swamp than it is to walk on fresh pavement. Let's fast forward 5 more seconds. Okay, this guy's right there, second guy, third, fourth, fifth one. Now the sixth guy, he's in the swamp as well, so he's slowed down. Not because he necessarily wanted to, but because it's harder to walk in the swamp. You can't move as fast in the swamp as you can move on the pavement. The last guy is still in the swamp, so he's still moving forward, but he's still going slower as well. Let's fast forward 5 more seconds. 1, 2, third guy. Fourth guy, he's kind of just going in there. Fifth guy is definitely in the swamp. Sixth guy is still there. Seventh guy, he's still there. We join these together. Again, we're looking at them from above. This is what we see. On the pavement, if we treat this as a wave, on the pavement, this wave was going this way. But in the swamp, the wave front was going this way. Why did it change direction? Well, because when it went from one medium to another, it changed speed. Waves do that. Okay, this is an analogy to just help us see that. But in the end, waves do that. When waves go from one medium to another, they will change speed. They're either going to speed up or slow down. In this case, they slow down. Because they slow down, they change direction. If they sped up, they'd also change direction, but it would be a different change in direction. Notice one other thing that changes here. It went from one medium to another, the speed changed. Obviously, it slowed down. The direction changed. What else changed? If this is the distance between a crest and a crest, we would call that our wavelength. Take a look at the distance between crest and crest right here. The wavelength is decreased quite dramatically. So when a wave goes from one medium to another, it will change speed. As a result of the speed changing, its direction will also change. As a result of the speed changing, its wavelength will change. That process is called refraction, the bending of a wave when it goes from one medium to another, the bending of light when it goes from one medium to another. When you stick a pencil in a bucket of water, it looks like that pencil's bent. It's not bent. Of course we know it's not bent. It just looks like it is. Because our eyes, our brains aren't smart enough to see what's really happening here. When light reflects off of the pencil, the part of the pencil that's in the water, and comes back and hits the boundary between the water and the air, it bends, it changes directions. But our eyes and our brain can't see that. Our eyes and our brain think that the light traveled in one direction. It hasn't changed direction. So for us, that looks like the pencil has bent. It hasn't. Rather, it's been the light that's bent. But our eyes and our brains think that light can't bend. So it looks to us like the pencil has bent. Refraction is that bending of that wave, or specifically the bending of that light. Here's a new term that you haven't seen in Physics 20. The index of refraction. The index of refraction is a ratio. Ratio is always divide, right? We learned that earlier on this year. You want to find a ratio, you divide two numbers. The ratio of my age to your age, about 2.5 to 1. Right? We divide my age by your age, and we get about 2.5. This is the ratio of the speed of light in a vacuum We're going to give the speed of light in a vacuum a new symbol. We called it V up until now. And now we're going to call it C, because we're also going to have another speed mixed into this whole thing. The speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. So it's the ratio of that speed of light in a vacuum to the speed of light in medium X. In other words, medium X is going to be the medium that you're in. The index of refraction of this medium is the speed of light in a vacuum compared to the speed of light in this medium. The symbol for the index of refraction is an n, a lowercase n. It's equal to C, or 3 times 10 to the 8 meters per second, over V, or whatever the speed is in this new medium, X. Now, the fastest light can travel is 3 times 10 to the 8 meters per second, Sergio. The fastest it can travel is that speed of light in a vacuum. So that number V, the speed of light in the other medium, medium X, whether it's air or water or glass or plastic or diamond or whatever, the speed of light V has always got to be smaller than C. It's either got to be the same as C or smaller than C. That means that the index of refraction will always be greater than or equal to what number? No. It's always going to be greater than or equal to 1. If the biggest V you can have is 3 times 10 to the 8, 3 times 10 to the 8 divided by 3 times 10 to the 8 is 1. V can be smaller than that, though. 3 times 10 to the 8 divided by 2 times 10 to the 8 would be about 1.5. That would be the index of refraction of glass, because light only travels about 2 times 10 to the 8 meters per second in glass, depending upon the type of glass. You solve for the index of refraction, you get a number that's 0.75. You're wrong. Do it again. Usually the index of refraction is somewhere in the range of 1 to 2. But every once in a while we can get something that's over 2. Diamond is 2.4, for instance. I haven't seen an index of refraction that's bigger than diamond. So if you get one that's 3.5, you're probably wrong. Try again. Now, we say that each particular material has a different index of refraction. It does, but in fact each material has several different indices of refraction. If we shine red light through a particular material, the index of refraction will be a certain value. If we shine blue light through that same material, the index of refraction will be almost the same value as it was for red, but not quite. The index of refraction for each material is different for each color, or at least slightly different for each color. Stop copying for a second and just look at the diagram for a second. If I shine white light, which is all the colors of the rainbow combined, that's what we see right now, right? White light. If I shine that white light on a prism, this triangular prism that's made out of, let's say, glass, then each different color will bend a different amount. The index of refraction determines how much light will bend. So if we have a different index of refraction for each different color, each color is going to bend a different amount. That means that white light that consists of all the colors will split up. It splits up into red, orange, yellow, green, blue, indigo, and violet. It splits up into the rainbow. That process is called dispersion. The phenomenon whereby white light splits up into its component colors because the thing doing the splitting up, the prism in this case, has a different index of refraction for each color. Where have we seen this? Sorry? Pink Floyd album cover, yes. Yes, I was thinking more of a rainbow. But sure, Pink Floyd album cover as well. You see this in a rainbow all the time. You don't have these little triangular glass prisms up in the sky. What do you have after it rains? Moisture, water droplets. What do the water droplets do? They essentially act as a prism. It splits up the white light into its component colors. Dispersion takes place, and we see a rainbow. I've also seen this in this school, really good example of this in this school. Haven't seen it very often because you have to be in the right place at the right time. But every once in a while, if you walk after school, okay, when the sun is over there and shines through those windows going into the atrium, every once in a while, it shines at just the right angle to go through those triangular glass display cabinets that we have. If it goes through the corner of that triangular glass display cabinet at the right angle, then it disperses. And it forms this rainbow. I've seen it a few times, this rainbow on the floor of the school. You walk past, and it's perfect. Red, orange, yellow, green, blue, indigo, and violet. You can make it with almost all the colors. It's perfect. But if you blink, pretty much you miss it. Why? Because 5 minutes later, the sun's going to be somewhere else and coming in at the wrong angle. So you've got to be there at the right time in order to see this. We've all seen it with rainbows, though, right? Okay, we've all seen it with real rainbows, that is. All right, I'm not going to ask you, obviously, to copy down this table. What this table shows, though, is the index of refraction for many different materials. Notice at the top, though, it says that it's for yellow light of wavelength 589 nanometers. Why do you think they specify that? Why don't they just say, look, these are the indices of refraction for air, ice, water, ethanol, and glycerin, and so on and so on? The index of refraction is different for each color. It's not dramatically different, but it's different. So it might be 1.33 for yellow light, but it might be 1.332 for violet light. As we go from red to violet, you can see that we have slightly increasing indices of refraction. Red has the smallest, violet has the most. Yellow is somewhere in the middle. So these values would be approximately the average value of the index of refraction for each of these different materials. But that number could be a little bit lower for red light. It could be a little bit higher for violet light. Okay, this number that's given to us for yellow light works for most purposes. We don't have to account for the difference for most purposes. Now we're going to talk about Snell's law, which is the relationship between the angle of incidence and the angle of refraction. The angle that it comes in at and the angle that it comes out at, relative to the speed, relative to the wavelength, and relative to the index of refraction. Draw a little picture here. Okay, there's my boundary between one material and the next material, and that dotted line is my normal line. This arrow is going to represent my wave, my beam of light, in the first medium. This angle right here, we're going to call theta 1, is the angle of incidence. The angle that it's going into the new medium at, relative to the normal line. This angle right here we'll call theta 2. It's the angle of refraction. The ratio of the sines of the angles, sine theta 1 over sine theta 2, is equal to the ratio of the speed in medium 1 compared to medium 2. It's also equal to the ratio of the wavelength in medium 1 to medium 2. In other words, as theta decreases, so does v and so does lambda. But notice it's equal to the inverse of the indices of refraction. It's equal to the ratio of n2 to n1. Why is that the case? Well, as theta goes down, v goes down. As v goes down, lambda goes down. But as lambda goes down, the index of refraction goes up. When you go from a low to a high index of refraction, you go from a high to a low speed. So v, lambda, and theta are all inversely related to n. Hence, lambda 1, lambda 2, v1, v2, theta 1, theta 2, n2 over n1. Now you can see there's 4 parts to this equation. You're only ever going to need to use 2 of them. Write down your givens, pick whichever 2 parts happen to fit. It's as simple as that. Mathematically, it can be a bit tricky because you're dealing with fractions here. But conceptually, it's no harder than anything else we've done. Write down your givens, see which 2 parts of that equation match up. Let's take a look at one example on page 668 here. Yellow light, they tell us it's yellow light because that's what they gave us the indices of refraction for. It's traveling from water into crown glass. The light rays are incident on the crown glass at an angle of 35 degrees. What's the angle of refraction? It's going from water to crown glass. It's going from the water to the glass at an angle of 35 degrees. We're going to call that theta 1. If we look at our table, we know that the index of refraction of water is 1.33. And the index of refraction of crown glass is 1.52. If this ray of light is going from an index of refraction of 1.33 to 1.52, what do you think is going to happen to it? Speed up or slow down? It's going to a higher index of refraction. It's going to slow down. If it slows down, v is getting smaller, so is lambda getting smaller, so is theta getting smaller. We want to solve for theta 2. We drew the angle here, theta 2, towards the normal line, bending towards the normal line because we're predicting that that value should be less than theta 1. Let's get the value for it now, and let's see if we were right. Let's say sine theta 1 over sine theta 2 equals n2 over n1. We don't need to worry about the lambda and the v. It's all part of the equation, but remember we said we only ever use 2 parts. Whatever 2 parts fit the givens the best. Say sine 35 over sine theta 2, whatever that is equal to 1.52 over 1.33, n2 over n1. Take the 1.33 up by multiplying. Take the 1.52 down by dividing, and take the sine theta 2 up by multiplying. So we're basically cross-multiplying everything. 1.33 goes up, this goes down, this goes up, and this is what we end up with. Let's do this as a class to make sure we can get the right number for this now. $30 degrees? 30? Let's say 1.33 divided by 1.52 equals 0.875. Let's multiply that by sine 35. We get 0.501879. Now, how do we get that into theta? That's sine theta 2. To get that to theta, second function sine works out to be 30.1 degrees. So, we were going from a low to a high index of refraction. We knew that light should slow down. If light slowed down, then the angle should get smaller. It did. It got about 5 degrees smaller. Okay, that seems perfectly normal. Okay, I get a number that looks like that. Okay, I'm pretty sure that I've done this question right. I get a number that's bigger than 35. I know I've done it wrong. What if I got a number that was, say, what if I got a number that was 12.2 degrees? Pretty good indication that I've done that wrong as well, right? I haven't changed the index of refraction that much, so the angle won't change that much either. Nick?
You just, as far as like the,
Yep.
you just take 1.52 divided by 1.33 and put that in brackets and throw it under sine 35.
Not throw it under sine 35, just throw it beside sine 35. If you calculated, if you got this number, okay, instead of, we took them over one by one, right? If you calculated that number, you're going to get a certain value right here. You take that over to the other side by dividing. So it would be sine 35 over whatever that number is equals sine theta 2.
You just do sine 35 divided by
Yep,
bracket.
yep. Yeah, you could, yeah, absolutely. Yep. Same thing. Is that okay? Okay. Here's your homework for tonight. The worksheet that I already assigned. In addition, page 668, questions 1 and 2. I want to give you a taste of this tonight, but I recognize that you got your worksheet, which has, I think, 7 questions on it, and a couple of them are kind of tricky, so I don't want to give you everything here. Just enough to give you a taste of it, just to make sure you're okay with it, and then we'll move on with it tomorrow.